During this session, we're going to talk about lending to the poor. There are a number of facts that characterize credit markets for the poor in developing countries. I'm going to first briefly summarize these facts and then try to write down a model that may help explain them. I'll begin by writing down a simple model of borrowing and then extend this model as required so that the predictions of the model match the facts we observe in the real world. So, before we move on to the model, let's talk about what those facts are. The first important fact is that the poor are often unable to borrow from formal lenders. A second important fact is that in the informal market, lending rates are much higher than deposit rates. Yearly interest rates are often found in the range of 40% to 200%, and we have examples of individuals and some studies, such as one involving fruit vendors in Chennai, India, suggest that interest rates may be as high as 5% per day. Our third fact is that interest rates are highly variable. Research in Pakistan by Aleem suggests that there is extreme interest rate variability even within the same village or town being studied. A fourth fact is that the rich have larger loans and pay lower interest rates than the poor. One summary report on informal lending in India shows that in the rural sample, the landless pay interest rates varying between 28% and 125%, while cultivators pay between 21% and 40%. Indeed, credit limits are often explicitly set to be proportional to the borrower's net worth. A fifth fact that we want to match in our model is that those who borrow more typically pay lower interest rates. And finally, the sixth fact about lending to the poor that we would like to match with our model is that default rates are quite low. People often borrow for investment, not because they're desperate. So, what sort of model do we need to explain the 6 facts that I've outlined? Let's begin with a simple model. Suppose there's a D% risk of default on any loan. Next, suppose we have gross interest rate, capital R. We assume we're in a competitive market, so the banks are making no profit. Then, for a given loan amount, this expression shows the amount that will be repaid to depositors. Where does this expression come from? Well, with probability D, the borrower will default on the loan and repay 0. And with probability 1 minus D, the borrower will repay the amount required, R. Given this expression, D times 0 is 0, and so the expected amount returned to depositors is 1 minus DR, the gross interest rate. In this model, the expected marginal product of capital must be equated to 1 minus D over R. What does this mean? It implies that individuals are only willing to borrow if they expect to earn at least 1 minus D times R rupees from each rupee that they borrow, because this is the amount that they're expected to repay. Given this, individuals will continue borrowing until they earn exactly 1 minus D times R from the final rupee that they borrow. As their marginal product falls below this value, they'll no longer be interested in borrowing. So, how does this model do in explaining the facts? Let's return to the 6 facts we started with. Well, does this help us explain why the poor cannot borrow from formal lenders? No, not really. This doesn't say much about formal versus informal lending. How about the fact that interest rates are high? Well, the model did discuss interest rates, but all it told us was that we expect interest rates to be high when default rates are high, and vice versa. This is in contrast to our 2 findings, that interest rates among the poor tend to be quite high and that default rates are quite low. Moreover, in this model, there's no variation in the interest rate charged based on amount borrowed, household wealth, or any other borrower characteristic. So, let's move on to a slightly more realistic model and see whether it helps us to match the facts observed in the real world. Now, imagine the bank lends to an entrepreneur, which has a business, which will produce f of k if k units of capital are invested. A borrower who has wealth W will need to borrow k minus W rupees. And at the end of the period, he or she will need to repay k minus W times R, where k minus W is amount borrowed and R is the interest rate. In contrast with the initial version of the model, by spending cost H on the entire sum borrowed, borrowers now have the option of escaping without paying. In this version of the model, we also assume that there is a cost of capital, D, which lenders must pay to depositors. Now, let's solve the model. First, let's think about the borrower's decision. After the borrower makes f of k, he or she can choose to repay the loan. In that case, profits will be f of k minus R times k minus W, where R is the gross interest rate and K minus W was the amount borrowed. Remember, this expression is the total amount that must be paid by the borrower to the lender. Now, what is the borrower's alternative? Instead of repaying his or her loan, the borrower has the option of escaping. If the borrower escapes, he or she earns f of k minus the cost of escape, which we've defined to be h times k. Remember, we use k here instead of k minus w because we've assumed above that the borrower must spend cost h on the entire sum borrowed. If the borrower chooses not to repay the loan and instead decides to escape, he or she earns f of k, the amount earned from the business, minus hk, the cost of escape. Now, how will the borrower decide whether to repay the loan or to escape? Let's move on to the next slide. Using the two equations we wrote down on the previous slide, we know that the borrower will choose to repay his or her loan if and only if f of k minus r times k minus w, the amount earned in the state in which the borrower repays, is greater than or equal to f of k minus hk, the amount earned in the state in which he or she decides to escape rather than repay. Now, note that we can simplify this expression. First, we subtract f of k from each side of the equation. Then we're left with minus r times k minus w is greater than or equal to negative hk. Now, let's add hk to both sides. Next, moving to the bottom of the slide, let's add r times k minus w to each side of the equation. Then, we have that hk is greater than or equal to r times k minus w, which equals 1 plus little r times k minus w, based on the definition of the gross interest rate. Before we move on, let's simplify the inequality from the previous slide. We determined that the borrower will repay if f of k minus r times k minus w is greater than f of k minus hk. To simplify this inequality, let's first subtract f of k from each side. Now, let's add rk to each side of the equation. This gives us rw greater than rk minus hk. To simplify further, notice that we can rewrite this expression as rw greater than k times r minus h. Next, we divide through by w, giving us r greater than k over w times r minus h. Finally, we divide through by r minus h and put k over w on the left side of the inequality to make it easier to interpret. Then we have that k over w is less than r over r minus h. Let's return to the previous slide. Here, you can see the equality version of the inequality we just derived. K over w equals r over r minus h. You'll notice that this expression has an equal sign rather than an inequality. This simply reflects the fact that at the point at which k over w is equal to r over r minus h, the borrower is exactly indifferent between repaying his or her loan and escaping. If k over w is even slightly less than r over r minus h, then the borrower will choose to repay. So, what predictions come out of the slightly more sophisticated version of the model that we've just worked through? First, notice that borrowers will be rationed. How can we tell this from the expression? Well, k over w will be less than or equal to r over r minus h. This implies that k over w is restricted to be below some value defined by the interest rate in combination with the cost of escape. Suppose we define k star equal to w times r over r minus h. Then, note that any individual wishing to invest more than k star, and so borrow more than k star minus w, will not be permitted to do so. This suggests that borrowing will be rationed. Now, will there be differences in borrowing based on household wealth? Yes. As you can see from this expression, k star, the amount of borrowing allowed, is increasing in w. our measure of household wealth. However, there are a number of facts outlined at the beginning of this session that this model still is unable to match. Let's return to our set of facts to look at what's not being matched by the current version of the model. So, as I've just mentioned, we matched the fact found in the real world that the rich are able to borrow more. We're also able to match the fact that default rates are low, since in equilibrium, we observe no default in our model. Remember, the reason being that the amount of money lent is such so that individuals would always rather repay than escape and default on their loan. Nonetheless, we cannot match the other 4 facts we've outlined. Namely, we have no evidence that poor people are more or less able to borrow from informal lenders, that interest rates are high or variable, and that people who borrow more pay lower interest rates. Indeed, in this version of the model, the interest rate R is fixed and will not vary based on any borrower characteristics. To try to better match the facts about lending to the poor that we've observed, we'll add another dimension to the model. Suppose that the lender must fix an interest rate that's high enough now to cover both the cost of borrowing and a fixed fee C. What would explain the existence of this fixed fee in the real world? Well, it could be anything from the cost in terms of time that the lender pays to learn about the borrower and make sure he or she is trustworthy, to the administrative cost involved in keeping track of loan repayment over the course of the loan cycle. In any case, we can now write down the lender's problem as follows. R of k minus w, the amount of interest that the lender receives on a loan of k minus w, must equal d times k minus w, the amount that the lender must pay the depositor, plus c, the fixed cost of the loan that we've just described. Now, remember that the lender must set the interest rate so that the borrower still wishes to repay. This requires that R times k minus w equal hk. If the interest rate is any higher than this value, the borrower will prefer to escape with the money. Combining these 2 equations, we have d times k minus w plus c equals hk. So how much will the lender be willing to lend? Well, let's begin with our equation from the previous slide. D times k minus w plus c equals h times k. Now, let's subtract hk from both sides of the equation. Then we have d minus h times k minus dw plus c equals 0. Let's add dw minus c to both sides of the equation. Then we have d minus h times k equals dw minus c. Finally, let's divide through by d minus h. This gives us k equals dw minus c over d minus h. This expression for k tells us the maximum that the lender will be willing to lend to the borrower. What does this expression tell us happens if dw is less than c? Well, if dw is less than c, then k is negative, implying that the lender will not be willing to lend anything to a given borrower with wealth w. How does k vary with w? Well, we know that d is greater than 0. This suggests that as w increases, so does k. How does k vary with h? Well, as h gets larger, our denominator becomes smaller, and so k increases. Why does this make sense? Well, an increase in h tells us that the cost of escaping has increased. As the cost of escaping rises, the lender is willing to lend more because the relative attractiveness of loan repayment for the borrower has increased. So, how does the lender set the interest rate? Let's go through the math. First, let's use the fact that the lender sets R times k minus w, the amount of interest received on the loan, equal to d times k minus w, the amount of interest that the lender must pay the depositor, plus c, the fixed fee associated with the loan. Now, dividing through by k minus w, we have R equals d plus c over k minus w. Next, let's make use of the expression we just came up with for k. K equals dw minus c divided by d minus h. Plugging this expression for k into our interest rate equation, we end up with R equals d plus c divided by dw minus c over d minus h minus w, which equals d plus c times d minus h divided by dw minus c minus w times d minus h, where we've multiplied through by d minus h. Simplifying this expression further, we have that R equals D plus C times D minus H divided by WH minus C, where DW terms canceled above. Now, let's return to the previous slide. Here's the expression we just derived for the interest rate set by the lender. R equals D, the amount that must be paid to depositors, plus C, the fixed cost, times D minus H, where H is the cost of escape, divided by HW, where W is wealth, minus C, the fixed cost. Now let's take a look at the expression we just derived. Notice the presence of a multiplier effect. When D, the cost paid to depositors, increases, R will increase more than 1 to 1. If it were just for this term, it would increase 1 to 1, but notice that D also appears here in the equation. This expression suggests that interest rates charged to borrowers can end up quite high relative to the cost paid to depositors. What's the intuition for this multiplier effect? Well, when the cost of the funds goes up, the interest rate must go up to cover this cost. However, this in turn gives the borrower more reason to try to escape rather than repay his or her loan, so the interest rate must go up even more to cover this cost of monitoring. The upward pressure feeds on itself, or the lender decides not to lend at all. How does this version of the model do in matching the facts that we outlined at the beginning of this session? It does pretty well. Let's rewrite the expression for the interest rate that will be charged by the lender. So, let's look again at our expression for the interest rate charged by lenders. R equals D, the cost paid to depositors, plus C, the fixed cost, times D minus H, the escape cost, over HW, the wealth, minus C. Can this expression explain why the poor can't borrow from informal lenders? Possibly. If it happens to be the case that the fixed cost paid by lenders is higher for formal than informal lenders, perhaps because informal lenders are members of the community who are better able to monitor borrowers, then the result may be, then one possible result is that only informal lenders will be willing to lend to the poor. What about the magnitude of interest rates? Well, the multiplier effect we identified on the last slide suggests the interest rates may be a good deal higher than rates paid to depositors. What about the magnitude of interest rates? Well, the multiplier effect we just discussed suggests that interest rates charged to borrowers may be a good deal higher than the amount paid to depositors. Are interest rates variable? Yes. Notice that in this expression, the interest rate will be lower the higher an individual's wealth, W, or the higher that individual's cost of escaping, H. Will the rich borrow more? Can this model explain why the rich borrow more? Yes. Remember from a couple slides ago, we showed that the lender will only be willing to lend up to K equal to DW minus C divided by D minus H. This expression suggests that K will be increasing in W. Do people who borrow more pay lower interest rates? Again, the answer is yes. Remember from the previous slide, we made use of the expression R equals D plus C over K minus W. Here, we observe that as K increases, the term C over K minus W decreases, and so the interest rate falls. Finally, are default rates low? Yes, as before, the interest rate is set so the borrowers will never prefer to escape and default on their loan rather than repaying it. Hopefully, going through these models has helped provide a framework to understand the facts outlined at the beginning of this session that characterize the credit markets faced by the world's poor.